Uh, uh, right. Hopefully everyone can hear me. So today the topic I will review is 3D human pose estimation from monocular RGB inputs. In case you're not familiar, I will go through the definition of this topic very soon. These are the contents I will go through in this presentation. So what is human pose estimation? Roughly speaking, human pose estimation is the prediction of body size and joint positions of people from the input. When we say input, we usually refer to the single image or videos obtained by the single lens camera. You can see the examples of the 3D human pose estimation here, where there is a single picture of a soccer player used as an input, and it outputs human body model with same size and pose of the person, which is rendered in 3D mesh. This technology can be used in many areas, such as 3D movies and animation industries, virtual reality, sports player analysis, action predictions for security, and so on. If we were to get more extensive, there's also a multi-view 3D human pose estimation, which uses multiple viewpoints instead of one, or other sensors such as depth and point cloud, wearable sensors, radio frequency, and so on. But we will not go through those today and focus on the single viewpoint RGB camera, which is most common in terms of using in reality and the open datasets. As written in the slides, monocular RGB inputs refer to the images from single lens camera with red, green, and blue colors. And when we say that we will do 3D human pose estimation using this input, it means we will obtain 3D outputs from the single 2D image inputs. So to begin with, let's briefly talk about the different types of inputs used in human pose estimation. The most common one being used is an image taken from a single lens camera, which is called a monocular RGB image, which is just an image from a single lens regular camera that all of us are familiar. In order to better predict the depth information and occluded regions, multiple cameras with different viewpoints can be used as well. There are also other sensors that can be used, such as depth point cloud sensors, IMU with monocular images, radio frequency devices, and so on. There are many different methods and approaches that perform human pose estimation, and they are all simultaneously making advancements since they all have pros and cons with different purposes. To begin with, let's talk about top-down and bottom-up approaches, which are the main two approaches of the 2D human pose estimation that are both still valid. The difference between the two approaches is that the top-down approach first detects every person in the image and then crop each person to perform the pose estimation one person at a time, while the bottom-up approach detects all the body joints in the image and then connects all of them by their relations to make body poses. These two different approaches have their own pros and cons. The top-down approach tends to be more accurate compared to the bottom-up because it takes care of one person at a time, usually with more in-depth cascading but slower. Since bottom-up has faster process that can take care of multiple people at once, the bottom-up is good at post-estimating multiple people in the video in real-time manner. As mentioned, they both have their own strengths and weaknesses, so nowadays they are both being used for different purposes. One example of the top-down approach is deep pose, which is one of the early human pose estimation used in deep learning. It first detects a single person and crops that part of the image and resizes it to its dimension. And then for the initial stage, it estimates all 16 key joints of the person in the image by direct regression. Then for the next stage, it crops the smaller bounding box of each joint and do more detailed estimation on each joint. They call this process cascade of pose progressor. Next, open pose would be the good example of the bottom-up approach. It is one of the strongest 2D real-time multi-person human pose estimator around. First, it predicts all of the human joints in the input image using the part definition, part confidence map, also known as a heat map. Heat map is representation of the probability of joints being around that place instead of pinpointing the exact location of where the joint might be. Then by using the part affinity field, so basically graph model and CNN, it uses the information of the relations among different body joints and connects them accordingly to make a human form. That was 2D human pose estimation. Now let's move on to the 3D human pose estimation. For the methods of 3D human pose estimation, it can be divided into two different types, model-based and model-free method. Unlike 2D human pose estimation, where the shape and length of the body is constantly changing based on the viewpoints and motions, the 3D human pose estimation can estimate the length and shape of the human body in 3D rendering. So it can utilize the 3D model that can fit the estimated poses. But first, let's talk about the model-free methods. The 2D to 3D lifting method is perhaps the most popular method being used. It infers 3D human pose from the intermediately estimated 2D human pose. So it only adds depth information to the 2D pose. This method is popular because it can utilize the excellent state-of-the-art performance of the 2D human pose estimator with their mass amount of dataset. One of the problems of the 3D human pose estimation is that they don't have much outdoor in the wild variety of datasets. So this characteristics of being supplemented by 2D dataset is very advantageous at this moment. This 2D to 3D lifting method usually outperforms direct estimation method that will be mentioned next. The direct estimation method directly estimates the 3D human pose from the 2D image in the end-to-end manner. A variety of different networks are being introduced in this method, and they are continually progressing. This method has the advantage of being end-to-end, so as the 3D human pose estimation datasets gets richer, it will most likely become more powerful in the future. This is one of the example of the early 2D to 3D lifting method. After estimating the 2D human pose from an image, and then adding the depth information to it by matching the 2D results to the 3D pose of the 3D pose library. Although this seems very simple and doubtful, it works surprisingly well because the 2D human pose estimation was accurate enough even during the occlusion. Although there isn't much to learn from this method, this is a good example of a strong performance of 2D human pose estimation carrying the performance of the 3D human pose estimation in 2D to 3D lifting approaches. Now, more common method would be to use a dataset that contains matching 2D body pose and 3D body pose so you can directly learn how to convert 2D pose to 3D pose instead of referring to a pose library. Now for the model-based method, there are two types of models, kinematic and volumetric. The kinematic body model is a skeleton-like representation that is made up of bones and joints of kinematic constraints. The volumetric model can recover high-quality human mesh, providing extra shape information of human body. One of the most popular volumetric model is SMPL-based, shown at the slide at the very right. One of the most popular some of the other examples are the cylinder man model used for occlusion reasoning, atom model, bone level skin model of human mesh, and so on. The advantage of using the model-based method is that it returns the realistic body shape at the end. The model-free methods are focused on accuracy of each body point, each body joints that it sees, so they are not considering how the body shape ends up to look like at the end. Their body model may have unrealistic body ratio or over asymmetric results, unrealistically twisted results, and so on. By using the model-based method, it has the information of the human body size and shape from the beginning, so it can end up having very realistic looking results. For the model-based method, one example may be simplified that uses SNPL body model. First, it predicts the pose in the 2D to 3D lifting manner and fits the 3D model appropriately to the results. The 3D model's shape is determined beforehand by the shape and size parameter found. Now, finding human pose for a single frame of an image is powerful enough, but when applied to a video, the prediction tends to shiver and jiggle excessively. There are many frameworks that are being used to smooth this out, and one example is using the GAN like Vibe did. Vibe is a Vibe is a video inference for human body pose and shape estimation, and it uses SNPL model, so it is model-based. After finding the human pose using the model-based 3D human pose estimation, it connects all of the results sequentially using a double layer of GRU, and then uses discriminator that learned from the real human motion capture data to discriminate whether the sequential result seems realistic or not. This process not only smooths out the motion of the result, but also adjusts the accuracy of the estimated pose in occlusion and self-collision. Let's briefly talk about the datasets. For the 2D dataset, the pen action, pose track, insta variety, and kinematics 400 are all good to be used. The pen action and pose track has ground truth joint locations annotated, but the insta variety and Kinetics 400 uses pseudo ground truth dataset annotated by 2D key point detector. For the 3D dataset, the 3D PW, MP, MPI, INF, 3D HP, Human 3.6M, and MS are some examples. They all have their own characteristics, but to put it short, the 3D PW and MPI is in the wild benchmark dataset for 3D human pose estimation, and Human 3.6M is a benchmark in the controlled environment. Usually for 3D human pose estimation, many datasets are used to train the model because fundamentally there is not enough labeled dataset for the 3D human pose estimation. We want to get as much data into it as we can. For the 3D dataset, the annotations all look similar to the example shown at the right. This is the typical evaluation metric of the 3D human pose estimation dataset. The MPJPE, PVE, and PCK are all widely used metric in this field, which basically measures the distance between the ground truth joint locations and the estimated locations. So the smaller the better. For calculating MPJPE, it first lines up the ground truth pose and the estimated pose by aligning root joint, which is typically a pelvis, and directly calculates the distance between the ground truth and estimated values. For the PCK, it counts how many estimated joints are within the certain range of the ground truth joint. They usually use either person's head size or overall height to calculate the radius of the correct area. This is what I prepared for today. If you have any questions, please feel free to ask me now or later. Thank you for listening.